Poonam, your voice is blocked, muted.
Okay, sorry.
Yeah.
Hello, everyone. So, we are in the sixth and final week of the workshop, and I strongly believe that all of us are enjoying the workshop and also learning from this workshop. And today we have the 16th lecture of this workshop, and it's our pleasure that we have Dr. Sarkar as a today's speaker. And without wasting of time, I request to Dr. Sarkar, please start the lecture.
Yeah. Okay. Thank you. Okay. Is the screen visible now?
Yes.
Okay. Great. Okay. So today what we are going to do is that we will just see some versions of mean value theorem for multivariable calculus, and you see some applications of this at the end we'll see how it leads to the Taylor's theorem for higher dimension. Okay, so yeah. Okay, so usual mean value theorem, what you have seen, that doesn't kind of spell right in higher dimension. So the problem is more or less, let me just show you first the corollary of this mean value theorem, what we are going to look at. So this one looks more or less exactly the same. So usually in mean value theorem, what you look forward to is some kind of that if there is a function has nice property, that is it's differentiable in open interval, is continuous in the corresponding closed interval, then pick any two different points in that interval, that and the difference, average of the difference turn out to be some derivative of some point, and that point turns out to be something in between those 2 points. Okay, so the usual mean value theorem. Okay, so this must be the correct form if I'm looking at it. So in this case, the function is a to r, and then again you are looking at some kind of difference between those 2 points. And well, I mean, averaging doesn't should make sense over here, because in the real case, you would be just looking at fa plus h minus fa divided by here the derivative itself is a linear map, so derivative has to be evaluated at that point. So this is kind of the more or less usual form, but the problem is the dimension of this range. Okay, so in the tutorial you will see an example of a function which is from usual circle rotation function, which is ft going to cos t sin t. If you just apply your thought over there with the closed interval 0 to pi. Okay, so in that case, you will see that this fails there. The usual version of mean value theorem, if I just try to force myself to think whether this happens, that is no more true. So this has to do with the dimension of the range space. Okay, so here is a correct version which you would see the mean value theorem. So what you start with is usually would be always talking about a function. So I will not be mentioning this always. And to make our life slightly easier, I will always assume that domain is an open subset. Okay, because earlier we were talking about domain is not necessarily open, but you take a point and some sufficiently small enough neighborhood of that is contained in, so that I can talk about limit and derivative and so on. And but the problem is most often you basically end up seeing some neighborhood around that, and whatever points you are actually considering, if you take union of those, it turns out to be again another open set. This is the union of neighborhood. So it's better to consider without losing generality, just take an open subset. That's good enough. Okay, and okay, so A should be an open subset of Rn. So domain is some portion of Rn, and my range is Rm, not necessarily m is equal to 1. And now the mean value theorem, the first version is as follows. So if you have, so in likewise in usual mean value theorem, you need to assume the differentiability. Okay, so this is no different. Here you have to assume the differentiability. And then what you would start with, you would basically pick up points A and A plus H so that both of them are inside A. Okay, and mean value theorem is, usual version of mean value theorem is one dimensional. So in that case, if you had a closed interval and 2 points inside it, or even open interval and 2 points inside it, the line segment joining those 2 points are always by default inside that open set. Okay, so I need therefore a little more assumption over here. So usually that is not true for arbitrary open subsets of in hard dimension. Like you can take a open set like a horseshoe and two extreme points. If we try to join them, they won't, the total line what you get, you won't be able to see it inside that open set. So usually if you want a full generality of these statement, that always pick couple of points, then the line segment joining them, closed line segment joining them should be inside that. This condition is usually called convexity. Okay, but for mean value theorem, we don't need that much. What we just need is take 2 points where I'll be considering the mean value theorem. So A and A plus H, and assume the line segment joining them is contained in A. This is at best we need. We don't need more than this. Okay, so let me just talk about the line segment a little bit joining this too. So usually this is called a convex combination of these 2 points. So if you take arbitrary 2 points A and B, the way to produce the line segment is t times, you basically take a convex combination of these 2 points. So you take any real number t between 0 and 1, take t times the first point and 1 minus t times the second point. So then if you consider all such possibilities, you end up getting all points between, strictly in between these 2 points. So here, because my second point is of the form A plus H, if you just correctly open up these expressions and write it properly, you will end up seeing that this is of the form A plus TH, where T is between 0 and 1. Okay, so what we need is that 2 points of the form A and A plus H, so that the entire line segment joining this two is contained in my open set A. So the mean value theorem asserts that then the moment you pick a point from the range, the vector from the range of this function, that is over here, then you take a dot product of that vector with the difference value of f, then it turns out to be the dot product of w along with the usual form, the derivative at some point evaluated at h. Okay, so if I just forget about my dot product and w over here, this is the usual version of mean value theorem. Okay, so you'll see later that this is kind of necessary. And of course, as a corollary, the second version what we showed you, this is easily deducible from this. If you, in a particular case, if you take m equal to 1, then for the vector 1, so this becomes a scalar. So the scalar 1, for the scalar 1, you should be able to find a t naught, so that this happens. And then you end up getting the second version of this mean value theorem, which is a corollary of this. Okay, so why do we need this for? You'll see next a couple of exercises we'll be perhaps discussing in the tutorial, and where you will see that mean value theorem fails. And this is why I wanted to show you that this is kind of what you are the expect in the full generality. Okay, but the next thing is, most likely what we are going to need is the version where m equal to 1. So I'll be coming to that in a short while. So let's try to see the proof, go through the proof of this, because more or less the kind of techniques what we do over here is going to be followed throughout this lecture for the rest of the proofs. So, okay, so one of the property of open set here we are going to use. So that says that if you take a closed interval joining A and A plus H, then I should be able to stretch it a little more. So it's here the condition is between t between 0 and 1. So if you think this closed interval turns out to be something like a closed set inside A. So one of the best way to think of this is there's something called normality property in topology. So closed set, you can always bound it by a open set slightly stretched out about it. So if you try to stretch it slightly more, you end up getting some little more on the left, little more on the right. So I can just minimize by the same constant over here. So that means I should be able to take something looking like an open interval instead of a closed interval in n dimension, which is of the form u epsilon. So what we did, instead of taking t between 0 and 1 strictly, starting from 0 and ending at 1, I stretched it on the left to minus epsilon, on the right I stretched it to plus epsilon. So then this closed interval is actually contained in this open interval. Well, there is no point to think that this is an open set. Of course, u epsilon is just a kind of a line stretched it. Around the end there are open ends, but still this is not an open set. But I don't need kind of an open set. The reason what we made this is because we wanted to use our usual mean value theorem somehow. So that is good enough in case you just try to connect it with an interval. So how do I do this? Because I have these open interval minus epsilon and 1 plus epsilon here. The first thing comes to our mind is define a function phi t, which is of this form, w dot f of a plus th. Okay, here this w is a vector from the range which is already given to you, and for this you are trying to produce certain thing. Okay, so if you take this phi t, the first thing you should be able to, what you need to compute and notice properly is that derivative of this is same as the dot product of w and f prime a plus th evaluated at h. Okay, so this is more or less the usual observation. What you can do is either you can directly check, or otherwise you can try to yeah, so here what I'm doing is I will just try to put the limit on and the direct observation how to do this. So if you just do this, you take a dot product, and this dot product comes out of the limit because of either the direct observation, the Schwarz inequality. If you apply Schwarz inequality, you will be able to see the limit actually comes out of the dot product. You don't need continuity or anything over there. But yeah, so that also is one possibility. Dot product with w, you can think it like a continuous function. Okay, but whatever it is, you get it out, and then you observe that this one is nothing but the directional derivative of f at the point a plus th in the direction h. So if you just try to open it up, t plus lambda minus t, and then cleverly you just separate the variables, and then you'll see immediately this one. But in the previous lectures, you have seen already the fact the directional derivative of f at a plus th evaluated at h, if f satisfies nice conditions, that is, it has to be differentiable, then it is the derivative evaluated at h. So this is what I wrote down. Okay, so what we end up getting is my phi is defined like that on an open interval, and it's differentiable on that open interval itself. Remember, I am always using the fact that f is differentiable on the entire A, not on the segment or anywhere. On the entire A, I should be able to speak of what f prime is. So I was flexible to do this, even if it stretched a little bit, epsilon on the left, epsilon on the right, no problem. Okay, now if you just almost immediate from the usual mean value theorem. So usual mean value theorem says that if I have a closed interval where the function is continuous and you have an open interval where the function is differentiable, then there must be a point where so the average of these two is equal to the derivative of that function at a point in between those two ends. Okay. So here, if I just apply this, this is the big part I'm going to use. I'm going to, here we have a little more, slightly more than what we expect, that the function is both continuous and differentiable between every point 0 to 1. Okay, the function is of course differentiable slightly on left of 0, on right of 1, so that differentiability at these endpoints are not one-sided differentiability. It's a proper differentiability, and this makes sense. So then the usual mean value theorem says phi 1 minus phi 0 should be equal to phi prime t naught for some t naught between 0 and 1. And if you just evaluate your values with respect to phi, you end up getting the exact result what you are looking for in this theorem. So this phi 1 minus phi 0 is just the difference of these two. If we just take the dot product outside, and phi prime t naught, we have already proved this is this particular value. Okay, and then the next corollary and application is this. If you take m equal to 1, you end up getting the same as it looks in the usual mean value theorem, because you start with the w equal to identity element on R, and then everything goes through. The dot product becomes the scalar multiple of two real numbers, and then everything is as usual. Okay, so these two are the versions of mean value theorem in higher dimension, and of course there are other versions also. So for our need, what we are going to do is that you're going to apply certain things around. So for instance, we'll be able to see some kind of another version of mean value theorem, which is a two-dimensional analog. So this one is mean value theorem, some kind of on an interval. So this is what a and a plus h would mean, even the previous one, on an interval. So the second version would be some kind of mean value theorem averaging done on a cube. So that is going to be required for when I want to show the equality of mixed partial derivative. So that's what we are heading to. So why do we need to talk about equality of mixed partial derivatives? So there are some benefits. Let me just discuss that. So first of all, the derivative turns out to be linear map. So it's always a kind of a issue, because well, I could immediately compute what is the derivative, but in calculus, usually what you have seen is that you should be always be able to talk about the derivative of a derivative if it's possible, and the third derivative and nth differentiability. How do we make sense of this? So the problem is, if it's a linear map, f prime at one point, the f prime turns out to be a function from A to the space of all linear maps from Rn to Rm. Now this right side is already a mess. This is, well, this is a vector space, but at best what you can think of is you just identify this with the space of n plus m dimension, right? So sorry, mn dimension, yeah, sorry. So this should be mn, not m plus n. Yeah, so that's a typo. So space of all matrices, that could be identified with this one. And then I can think of f prime a being a matrix over there. Now the point is, to do analysis, it's better you try to identify things with real vector space canonically looking like a product of real lines. Okay, so if we try to do that, this mat m cross n, this is the space of all matrices, that doesn't quite look like exactly r to the power mn. because this should look like there is a proper order of stacking of the rows. So the first row comes first, and then second row comes second, and then there should be a particular ordering. If you mess with that, there is a real issue, because there is some kind of canonicalness about where f prime is going to. Now, if I try to do the same for the second derivative and so on, I have a very messy notation here, and that is going to be difficult to talk of. Am I still audible? Sorry. Hello?
Yes, sir, you are audible.
Okay. So I thought I just logged out by somehow. Okay. So this is, so usually the higher order derivatives are something like we think of he who should not be named. Like you say that he exists, but you should not name it exact, or you shouldn't ask like what is the exact value or something like that. Okay, so yeah, so everywhere you just replace this n plus m by mn, so that should be the product. So the best way to talk about the higher order derivative, if I want to talk f power k, is that we already found a way out. It's called partial derivatives. So f prime exists, assure the existence of f prime, I would just make sure that the partial derivatives of the component functions exist and they are continuous. Now, if I want to talk about the second derivative, so instead of talking about the second derivative, what we can do is that let's directly try to think of the partial derivatives of the component functions which are actually looking like partial derivatives. Okay, so you start looking at djfia wherever it exists, and then what you do is that treat these djfia being certain components. So djfi, I treat it as a function, and then I look at the derivatives, partial derivatives of these functions. So that is dr djfia, and again I keep on doing this. Okay, so what's the benefit? So benefit is you will see that assuring again that these second order derivatives exist and they are continuous, it's going to ensure that the second derivative of my original function also exists. So this is nothing less than what you already have seen. Okay, so let's think a little bit on this. So the only problem of defining this was f prime is going to somewhere, but the image of this look like a matrix whose entries you have to properly label. Like djfia should means ijth place in the matrix. Now, if I try to do something like dr djfia, so that means I'm looking at fia going to hom r rn to rn, something like that. But then you end up seeing something like a three-dimensional matrix, and then some notation like this is exactly good for this. Okay, so instead of talking about that whether my second derivative exists or not, I can simply just make sure that this partial derivative exists and this is continuous at neighborhood of a. Then that is good enough to assure my second derivative of the original function also would exist. Okay, so this is why the notion of C1 or CK function is being made over open subsets. So you say that a function is of class C1 on an open set if all the partial derivative exist and those derivatives as a function are continuous. Okay, and then the CK differentiability should be that all these partial derivatives up to kth order should exist. So I should think of djfi and then make another drfi, then dr prime, drfi, and so on. I do it k times and I get several functions which are kind of there are orders involved, and then I can talk about all possible such functions. I need all of them to be exist and continuous. So then I'll say that this is of class CK. So a cleaner statement is simply you can just say that DJFI are of CK plus 1 on A. Okay, so this is a notion of CK differentiability, and then I would be looking at some expression like this. So whenever I'm looking at K order partial derivatives, this is like you first differentiate with JK variable, then you differentiate with JK minus 1 variable. At the end, you have you differentiate with respect to J1 variable. Okay, now the point is there are so many choices for J1, J2, JK, and our life should be easy if I can switch these two. So let's say dj1, dj2 are applied on some function. If I can make sure that this is equal to dj2, dj1, then what I can do is that whatever variables you are trying to differentiate with respect to, you just put them together. So for instance, if I know among these j1, j2, jk, one appears 3 times, I'll put d1 cube in the beginning. So I can just differentiate with respect, or d1 cube at the beginning. So this is the beginning and this is the end. So I can put it at the end so that it acts on the function directly. So I can make sure that partial derivative with respect to x happens in the beginning. So all these things we can do, and then the advantage is whatever the variables are there, put it together. You do the partial derivatives with respect to one particular variable, club it together if these are pairwise switchable. So that is one of the motivation to look for this interchangeability. And you'll see in Taylor's theorem, if you are managed to do this, in Taylor's theorem, the statement would look much nicer. Because remember, my kth order derivative in the usual calculus, where it appears in the Taylor's theorem, that is a very clean statement. But if you try to do it for the higher dimension, you need to arrange some nice way to write these things down. Otherwise, it's very difficult. Okay, so let's try to go to the statement of these equality. So what it says is that you take an open subset and assume that the function is of class C2. So what you need is both the derivatives dk dj and dj dk, all of these should exist and are continuous on every point of the component functions. And then for any a, you have this equality. Okay, so I kind of wrote down the general version, so I don't need to actually, if you look at it carefully, this I is kind of brought up unnecessarily. Well, just as a statement, it looks good, but it's as good as saying that take m equal to 1. Okay, so there is no, not too much glory in just putting m greater than equal to 2 over here. Of course, the statement is still true. Okay, but whatever is this, let's try to prove this. Let's try to go to the version of mean value theorem, what we are going to need. Okay, so what does it say? It says that you look at a function. So for this version of second order mean value theorem, we are not assuming the function is of C2, class C2. What I need is, so there are two statements. For the first one, I need D1F and D2 D1F should exist. Okay, so this is kind of good enough. So what it does is the following. You try to draw a cube with the perimeter points as follows. The lowest corner point is AB. This point is A plus H, comma B. Then I have B plus K, comma A. And then on the top corner, I have A plus H, B plus K. So basically, you start with one corner point AB, and stretch on the x-axis to h unit, h amount, and stretch on the y-axis to k amount for h and k positive. Okay, so then you draw a closed rectangle of that shape. So this is what I did. And suppose my closed rectangle is contained in A. Again, the mean value theorem, there was a line, here I am taking a rectangle. And look at this particular expression. It is some kind of two-dimensional averaging again, not averaging without the area. So if I divide this quantity by the area of this square, area of the square, then I'd end up getting the averaging. Okay, so what you do is that you look at the top corner point, subtract the two of the adjacent points to the top corner, and then add FAB to this. Okay, so there is some kind of alternating signs are there, but that is kind of justified because here you are looking at basically averaging, keeping the A plus H fixed. Okay, and here you are doing A fixed and you are averaging with respect to the second coordinate. Okay, so that is kind of makes sense on this in some sense. So suppose these two exist and my delta FC is kind of defined as this quantity, which is this divided by the area should be the averaging. Then this one says this is exactly equal to the area times d2 d1 f at certain point. Okay, and I expect the point to be strictly living inside that square. So the square is a closed square, closed rectangle, and the point I get is an interior point of this. Okay, so that is again some kind of similar analog of mean value theorem over here. So the only difference is I am trying to assume as less as possible. So for the first statement, I need that d1f and d2 d1f should exist. For the second, I need this d2 and d1 d2f exist, and similarly I get the averaging is on d2 d1f instead of d1 d2f. Okay, so once this is done, this proof is over, then what you would end up seeing is that in the final version of the Schwarz theorem, let's just try to prove this first. So what you would do is that here I want to establish the equality of these two. Okay, so again you start with a point AB in that rectangle and take the unique stretching factor T. So from that particular theorem, you see that the quantity on the left, what you see, the delta F computed on this cube CT, closed cube CT, turn out to be d2 d1 F at some interior point time the area of the rectangle, so which is T square. Okay, and then the second theorem also says that the second part of that theorem also says it should be d2 d1 d2 instead of d2 d1, but at a defined point, possibly xt prime yt prime, which is also an interior point. Now what you can do is that you can just take t divided by t square and allow this t to converge to 0. And then what you end up seeing is that if t converges to 0, this interior point, whatever is there in the rectangle, it slowly approach to the lowest corner point. Let's look at the picture again. So if I choose a point inside this rectangle, then as the perimeter's width and the height of this rectangle both converge to 0, this any point, not just the top corner point, any point living inside this would converge to the bottom point, which is basically AB over here. Okay, so that's what you would need over here in this theorem. So as t tends to 0, your xt and yt should converge to AB, Same with xt prime, yt prime, which are the interior points. If that happens, this turns out to be d2 d1 fab and d1 d2 fab. But both of them are equal to the quantity I'm looking at. So this immediately settles this theorem. Okay, let us quickly go through how do I prove this particular mean value theorem. So what we did is we again did something as similar to what we did in the previous theorem of the mean value. So we tried to stretch a little bit on left and right, and at this point both in the direction of x and y axis. So if you see that the black rectangle is my rectangle C, and then if you stretch it on the left and right a little bit, you end up getting these green dotted lines, and I want to look for u epsilon, which is the open set, which is essentially all points within these green dotted lines around this particular rectangle C only. Okay, so I'm just stretch a little bit to epsilon to the north, epsilon to south, epsilon to left, epsilon to right, and I form another rectangle, ignore the boundary points, and I end up getting an open set, which is open rectangle, which is u epsilon. So this is what I got. And then again, as what you did in the previous theorem, you try to connect it with the usual mean value theorem. So you want to define some phi. So in this case, you take phi to be f of t b plus k and subtract ftb. And then if you show that this is differentiable on this interval. So first, what you are trying to do is that you try to compute the derivative with respect to the first axis. Okay, so the first one we are trying to exploit d1 if exist, and then I'll go to d2 d1. Okay, over here, so therefore I'm looking at the first variable. So here first variable is a dependent variable on this function. If you compute the derivative, you see this is d1 f t b plus k minus d1 f tb. Okay, now if this is the one, then you define another second function, which is this difference, and then in the second level you again apply mean value theorem, and you end up getting this state. Okay, this is kind of very much straightforward. There is no surprise in this. First one layer of mean value theorem multiplied to the height of the rectangle, and then the second one, in the factor whatever you see inside, you try to define another aiding function, which is psi. Over here you apply the mean value theorem on this, you try to again transport it to usual mean value theorem, and then you get some expression like this and plug in over here. Okay, as we are saying, if I do all these things, the best part of this is I should be able to switch any two particular adjacent operators dji's, and then in that case I should be able to write something like this. For any permutation on n variables, I should be able to write my dj1 dj2 up to djk applied to some component function b with respect to these symbols being permuted by sigma. And in that case, I should be able to collect my d1s, d2s as the way I wish. I should be able to write down something like this. So this should be equal to d1 power alpha 1. So if d1 occurs alpha 1 times in these notations, then d2 occurs alpha 2 times, then you put d2 power alpha 2, and we have a much more cleaner notation than how it looks like over here, where you do not have any idea how to handle this. Okay, so finally this notation is would be very much useful when I want to talk about Taylor's theorem. Is there any question so far? Okay, There is no question. So let's go and finish Taylor's theorem. So the usual Taylor theorem, what you learn in calculus. So there are several versions of this. I think this one I got it from Rudin. So there is also something called an integral form and several complicated expressions. You can write it more complicatedly, but what is going on over here is that you take a closed interval, you assume it is differentiable up to k plus 1 times, but up to k times whatever you get, this is continuous. Okay, so the only difference is I could have removed this if I ignore the endpoints. So of course gk plus 1t exists will ensure gk plus 1t is continuous, but at the endpoints I'll have problems. So you write it like gk is continuous on the endpoints and gk plus 1 exists for every t in between. And then if you choose any two alpha beta in this closed interval, this pair of points could both be equal, or then there is no surprise, of course, or otherwise they could be coinciding with A and B, or otherwise I might end up getting something like alpha is bigger than beta instead of alpha less than beta, or several of these varieties can happen. Okay, so what you end up getting is I should be able to write G beta in terms of G alpha. So that's the target. So various expressions of G alpha, where beta might appear but only like a polynomial in the coefficients. So this is what is going on. I'm trying to write G beta in terms of G alphas. So then the second term would be the derivative and the difference. Then I'll get the other or higher order derivatives. And the last one is called the remainder term. So there should be a point C strictly in between alpha and beta. Well, I don't know alpha is bigger than beta or beta is bigger than alpha. So whatever of these occurs, then C is in between them, and you take the k plus 1 derivative, compute it at C, you divide it by this k plus 1 factorial, and this other part b minus alpha to the power k plus 1 is still fixed. So this is called the usual Taylor theorem, and the version you are looking at, the only problem with this particular version is this remainder term. So you need to do a little more thing to make sure that the remainder term stays small, so that if I try to talk about a function which is infinitely differentiable, I should be able to write a neat and clean Taylor theorem without remainder. So it's kind of look very regular Taylor form. Okay, so for this what you need is you need to make sure that the derivative does not misbehave. Here you assume that derivative exists, but in case your derivative become very oscillating, and then it's kind of, it need not be unbounded, but the bounds are too high, then you won't be able to bound this particular remainder or try to make sure that converges to a zero as k tends to infinity. That kind of thing would not occur. So you still need a lot of conditions on your function g to get nice expressions. But whatever, that was in general, in principle, the Taylor theorem. So what we are going to do is that we are going to talk about the Taylor theorem for a function a to r, where a is a subset of Rn for some arbitrary n. We'll deduce just from the usual Taylor theorem. So as you are seeing that everything is deduced from the usual theorems, like mean value theorem is deduced from usual mean value theorem. Here also Taylor theorem I'll just deduce from usual Taylor theorem. Okay, so you need little bit of again notion. So what you need, something called convexity. So you say a function, the subset, we call it convex the moment you join 2 points by a straight line in nth dimension. Join 2 points means you don't stretch the points infinite in the infinite direction. Sorry, don't stretch these lines to the infinite direction. It's just the line segment between those 2 points. So this is what I was talking about earlier. So then whenever you join these 2 points, set, I will say it convex if that segment always contained inside it. So for example, the closed and open balls in Rn, or even the irregular polygons, I don't need it to be regular. Only thing is I need to make sure is that these angles, internal angles, doesn't exceed pi. So otherwise you'll create a cornering outside and you can easily find a non-convex set. Okay, so that is convexity, what we are going to require. Next, I'm going to require some kind of notation. So what this is you, by n naught, I mean basically all non-negative integers. And for an n tuple of non-negative integers, I just define their mod of that tuple to be the sum of the entries. Okay, and then next notation is, if I have some ck class function, I'll be talking about coordinates, manipulating coordinates of the point from the domain. So I'll be writing something like this. So for a tuple alpha 1, alpha 2, alpha n, I'd be writing something like x to the power alpha, which actually means x1 power alpha 1, x2 power alpha 2, up to xn power alpha n. Because x is a vector and alpha is also a vector, x power alpha doesn't make sense. The notation is simply to explain this. It's a shorter notation to make sure that your Taylor's theorem looks nicer. Okay, and the second is, remember this is the notation he came across. Now after this, after we assume that there are FEs of class CK or something, yeah, FEs of class CK, then I should be able to switch all these derivatives in its right place, and then I should make sure that it look like d1 power alpha 1, d2 power alpha 2, dn power alpha n. So that's the meaning of d alpha f. Again, this is just to make sure the expressions doesn't become very huge. Okay, so what is Taylor theorem? The Taylor theorem in several variables says that you start with an open convex set and you just need the assumption that your function is of class ck and the mixed partial derivatives of order k plus 1 exist. Okay, so this is exactly the same what is happening in case of the usual Taylor theorem in calculus. So then for any pair of points which look like a and a plus h, I should be able to write a plus h, f of a plus h in terms of fa. So these means actually the d power alpha fa, these are the notations over here. You divide by factorial alpha. So okay, so there is a small problem here. So I should have explained another notation over here. Remember, this alpha is a tuple. So the factorial alpha actually means the product of factorials of its individual entries. So everything is non-negative over here. So there is no problem defining factorial alpha 1, factorial alpha 2 and up to factorial alpha n. You just multiply them and that's the meaning of factorial alpha. Third term over here is this h power alpha. So h is a vector and alpha is a tuple of integers, and I already explained this particular notation. So this is what h power alpha should mean. And there is some remainder term. Okay, so let's forget the remainder term. First, this term, when you are looking at it, you are looking at all possible tuples alpha, but up to what? So remember, in Taylor theorem in the usual form, you have derivatives of order 1, order 2, so that usually the nice form you have either f prime or f double prime or f triple prime, you can just write it like this. Here the problem is, even if I have combined them, I might have ended up getting two distinct tuples so that the sum is constant. The sum could be exactly equal to k, but still I have the values of alpha is are different. So for example, if I take all of them to be yeah, so you take the alpha 1 to be k and everything else is 0. So you end up getting d1 power k f. Then you take alpha 2k and alpha 1 and rest everything is 0. Then also you get d2 power alpha 2 and everything else just disappear. So there are lots and lots of possible ways to find out the kth order derivative. So for instance, if you take the second order derivative, you end up getting something like d1, d2, well, product of any two di and dj and the squares of di's. So di square f for all possible values of I and di dj for all possible pairs of values of ij distinct. So those are the two up to two order partial derivatives. So all these possibilities will appear in case you are looking at Taylor theorem in higher dimension. So this is what I mean by this term. If you are writing norm alpha less than equal to mod alpha less than equal to k over here, that precisely means all possible partial derivatives up to kth order, you sum it over here. And now let's come to the remainder term. The remainder term is usually represented in the usual Taylor theorem also. This norm of this is the represented as k plus 1th order derivative. So this is what you exactly did. Okay, and again the c represents a point between 0 and 1, which again resembles something like a point between a and a plus h in the usual, if you try to compare with the usual Taylor theorem. Okay, so let's not, so the proof is actually explained over here. I can just quickly go through over it, but let's try to see an example over here. So here's a expression fxy is x square plus xy plus y square. I want to write it in powers of x minus 1, y minus 2. Okay, so one very standard trick is you just try to set x minus 1 is u, y minus 2 is v, and then replace. So then x become u plus 1, y become v plus 2, and plug in these values over here, and then you expand. Okay, that's the best trick. Okay, but here what we want to do is that we want to explain what we learned in the Taylor's theorem over here. If you try to think of explaining the terms of the Taylor theorem to yourself, or if you try to see that what are those derivatives, partial derivatives in this place is doing here. So let's try to look at this example. So if you try to write these transformation, then my fxy turns out to be f of u plus v translated by the amount 1 comma 2. Now this extra 1 comma 2, you can exactly think it like my extra h over here. So it will exactly look like fuv and these derivatives computed at uv with these correct factorials and powers of 1 and 2, 1 comma 2. Okay, so let's explain this terms of k equal to 1, terms for k equal to 2, and immediately I can the conclude one thing is that if I have terms for k greater than equal to 3, that is going to vanish because any partial derivative of fxy of order bigger than equal to 3 must vanish, right? Because every term is quadratic over here, so they need to vanish. Okay, so then k equal to 0, I just have the usual term, which is the function. K equal to 2, basically to find out, sorry, for k equal to 1, you basically want to find out what are the partial derivatives with respect to u and v. So with partial derivative with respect to u is just d1f. This is what you can compute. It's 2u plus v and u plus 2v. Then the meaning of this first term over here is you look for all possible ways to write down order 1 partial derivative. Luckily, there are only two possibilities. I can only write d1f or d2f. If it's d1f, it's kind of thought of as my alpha in this particular case is 1 0, and if it is d2f, this is 0 1. So the power become the 1 2 tuple. I have power to the power 1 comma 0, that is 1 power 1 dot 2 power 0. The factorial also is factorial of the tuple 1 comma 0, that is factorial 1 factorial 0. Similarly, I can do the same over here. This is corresponding to alpha equal to 0 comma 1. You get 4u plus 5v. Next is for k equal to 2, there are three possible choices. You can do d1 d2, and remember there is no d2 d1, and then d1 square f and d2 square f. Okay, again once you compute this, d1 d2 should be thought of as the alpha corresponding to 1 comma 1, the tuple 1 comma 1. So that happens in the exponent of the coordinate 1 comma 2. So this is 1 comma 2 to the power 1 comma 1. That is the notation over here. So let me go back to the notation. This notation is basically 1 comma 1, sorry, 1 comma 2 to the power 1 comma 1. So that is 1 power 1, 2 power 1. Okay, let's come back to this. So this alpha 1 comma 1 over here. Again alpha 2 comma 0, I'll get this one. And if I take alpha equal to 0 comma 2, I'll get this one here. Remember, if the length is 2, how many ways you can think of alpha 1, alpha 2, so that the sum alpha 1, alpha 2 is 2. There are only three possibilities. The coordinates 1 1, 2 0, 0 2. In case I had 3, I'll have more choices. Like there should be 3 comma 0, 2 comma 1, 1 comma 2, and 0 comma 3. Basically two coordinates whose sum is equal to 3. Yeah, so if we have a problem which involves the cubics, there is a question given in the homework set. So you can experiment on that. So you have to go onto the cubic term and do a little more. Okay, so I think it's almost time. So what I'll do is that I'll give a rough sketch of what is done in the proof. So again over here, what you do is that you try to use a usual Taylor theorem or usual functions. So you try to transport everything to a one variable function. Okay, remember my function f is from a to r. Okay, so then if I just define gt to be f of a plus th, this turns out to be a function from the closed interval 0 1 to r. And then you try to compute what is g prime t. This is kind of more or less done, in which you have actually seen in the previous case. Okay, so only difference I have shown over here is, in the earlier case I just left it like this, f prime a plus th evaluated at h. But now if you remember, f prime a plus th, because my f has range the real numbers, this turns out to be just a vector, and you are looking at this f prime a plus th evaluated at h, meaning if I just write it f prime a plus th as a matrix, then this matrix as a vector take the dot product with this vector. Now the dot products are taken, so if I just expand f prime a plus th, this turns out to be these numbers, dj1f evaluated at plus th for various j1s. And if I take the dot product, I end up getting something like this. Okay, now the next challenge is to write down G double prime. So this is not so difficult. The only point is you have already computed G prime T, which you are going to use. You have a summation formula. What you do is that you simply push this summation factors, whatever you don't need, outside. So you end up getting some dj1s and the limit with respect to those dj1s. And then you end up getting a directional derivative. So if I just do this, you end up getting a second layer of summation. Okay, so because this is the full directional derivative at a plus th evaluated at h, again you have to consider all possible j2s. So there is a second layer of summation, and then what you end up getting is summation of something like this, hj1, hj2 and these derivatives. So finally, if we try to calculate for some higher order derivatives, it will turn out to be some kind of complicated expression like this. Now, where these notations which we are dealing with come from is as follows. You basically have fixed an h. So these coordinates are already known to you. And these j1, j2, jl are likely to vary among these possible values. In between 1 to n, this is like to switch. So you want to find out for which j1, j2, al I can put these together. Okay, put these together in a sense. Let's say these j1 and j2 are same, so I can just write hj1 square. And even better, if I just know that j1 equal to j2 equal to 1, then I could have written just h square. Sorry, h1 square. Okay, so for the quest of that, you have to find out how many repetitions of the same h1 is been occurring, how many repetitions of h2 are occurring, and so on. If I try to find out the occurrence of this turns out to be something called the multinomial formula. Out of the L choices, I suppose alpha 1 of them are 1. Then I am left with L minus alpha 1 choices, and I suppose alpha 2 of them are equal to H2. If I continue doing this and open up these combinations, you end up getting some formula like this. And this is the reason behind why in the derivative this product is coming up. And here, because I have written it like this, now I can simply apply, right, h1 power alpha 1, because alpha 1 h1 is occurring alpha 1 times. So similarly h2 is occurring alpha 2 times. I can write h1 power alpha 1, h2 power alpha 2, and so on. So this is the rationale behind this expression. And similarly, because of the switching of the partial derivatives, I can always prefer to write d1 power alpha 1 and then d2 power alpha 2 and so on. This is the rationale behind writing these expressions. So finally, the usual Taylor theorem applied to my function g, whatever you have defined, you just apply it and then nicely think how we get this. The usual derivatives turn out to be giving you terms, and that's it. The last comment is about this remainder term. If you want to control this, you need a little more assumption. Just ck and k plus 1th order derivative exists doesn't help. So what you need is you assume the class is also of class ck plus 1. The advantage is if it's of ck plus 1, then these derivatives are turning out to be continuous. So you will end up getting okay, so this was the remainder term here. So you end up getting a uniform bound for these functions because they are continuous on a closed interval. Okay, and in that case, you bound entire thing by this and get some again multinomial formula. You get something like that, and now this sum turns out to be the infinity norm. Okay, and then infinity norm you can easily bound it above by your usual square root norm, Euclidean norm, and then therefore you can bound it by this quantity. Well, usually people try to see if h norm h tends to 0, how these remainder term in which rate this remainder term is kind of going to 0, you can say this is a kind of a constant times the k plus 1th order of the norm. So that is the growth rate of this remainder. Okay, so that's it. I'll stop here, and if you have any questions, I'll answer.
So any questions from the participants? I think no. So claps for Dr. Sarkar.
Thank
So
you.
on behalf of all of us, I thank to Dr. Sarkar to cover the important theorems of real analysis with examples and enlightening us with his knowledge. And today lecture gave deep insight into the topic, and I am pretty sure the precious knowledge that Dr. Sarkar gave us will definitely help us in our studies and future. Thank you, Dr. Sarkar.
Yeah, thank you very much.